Hey everyone, thanks for joining us today. Here at NVIDIA, we're excited about the recently announced AI at the Edge challenge with Hackster, and to dive in with you into using Jetson Nano to create your own AI-powered projects. And after the presentation, we'll take your questions during Q&A. With that, let's get started a while. For those of you who aren't already familiar with Jetson, it's NVIDIA's family of embedded high-performance AI computers, often used to deploy deep learning and computer vision for autonomous robotics and AI at the edge. And with Jetson Nano, we made it easier than ever to get started developing your own AI applications, so we thought it would be a great opportunity to team up with Hackster to put on the AI at the Edge challenge. There are 3 categories in the competition: autonomous machines and robotics, intelligent video analytics in smart cities, and artificial intelligence of things. Each category will receive 3 top awards, including an all-expenses-paid trip to NVIDIA's GPIO Technology Conference in Silicon Valley in the spring, along with a chance to demo your project to world-leading AI experts at the event, and also a bunch of GPU hardware and cloud compute credits. There's also an AI Social Impact Award given to one of the projects among the 3 categories that receives the top prizes, and we will be awarding participants along the way with free hardware and online courses NVIDIA's Deep Learning Institute. Project submissions are due by the end of January, and we have a limited number of nanos to give away by November 15th, so with that, let's dive in a while. We launched Jetson Nano earlier this year, and it's our smallest, lowest power, and least expensive computer that NVIDIA's ever made. This is the Nano Developer Kit, and it's a complete embedded AI computer that has an NVIDIA GPU on board capable of 472 gigaflops of compute with full support for CUDA 10, a quad-core ARM 64-bit CPU, 4 gigabytes of RAM, and it's only $99. It's fully compatible with Linux and the NVIDIA AI platform. It's supported by NVIDIA's complete software stack, and it has the performance and power efficiency to run modern AI workloads, all in 5 to 10 watts of power and in a compact footprint. The DEVKit's built around the Jetson Nano Compute Module, which is a 45 by 70 millimeter embedded system on module that can be integrated into production products and devices. The Compute Module contains all the processing, memory, and storage on board, and it provides all of the I/O through its 260-pin SODIMM style edge connector, which a carrier board breaks out into the usable ports and connections. The DEVKit includes the pre-assembled Nano module, heatsink, and an open-source reference carrier board, which embedded system designers can use to design their own customized carriers that route the I/O to the peripherals and connections that they desire. Here's a closer look at the specs and features of the DEVKit. It has 4 USB 3 ports, HDMI and DisplayPort, Gigabit Ethernet, M.2 with PCI Express, MIPI CSI camera connector, 40-pin GPIO header including I2Cs, SPIs, and UART, and a micro SD card slot. The camera flex cable connector is compatible with popular MIPI CSI cameras like the IMX219 based Raspberry Pi camera module V2 and others that our imaging partners have created as well. The 40-pin GPIO header on the DEVKit is similar to the 40-pin header on the Raspberry Pi, which means you can use a lot of the same devices and accessories with it. There are 3 primary ways to power the DEVKit, which we'll discuss in detail later, all of which use 5-volt DC. You can use a micro USB charger, the DC barrel jack adapter, which is capable of delivering more power if you have a lot of peripherals plugged into the board, or power over Ethernet. The Nano DEVKit boots Linux from the removable micro SD card slot. The distribution of software for Jetson we call Jetpack, and the current distro is based on Ubuntu 18.04. The processor has an integrated 128-core NVIDIA Maxwell GPU, 64-bit quad-core ARM Cortex-A57 CPU, 4 GB of LPDDR4 memory, and 4K hardware video encoder and decoder, capable of simultaneously decoding 8 HD video streams and coding 4 video streams at once. Jetson Nano is made for processing lots of high-definition sensors and multimedia with AI and analytics. You can get these developer kits from a variety of suppliers worldwide, including Arrow, Amazon, Newegg, Seed Studio, SparkFun, and Silicon Highway, and through the challenge, you can get a $5 rebate through Seed Studio. As mentioned, Jetpack is our distribution of software that's available to run across the Jetsons, and it's based on Ubuntu Linux along with NVIDIA's driver, L4T BSP, and tools like CUDA. It's like a supercharged version of Ubuntu that comes preloaded with GPU-accelerated deep learning and computer vision libraries, along with multimedia tools for camera capture and the video codecs. You can easily install machine learning frameworks like TensorFlow, PyTorch, and Caffe on top of this, and robotics frameworks like ROS, and pretty much any of the programming languages that has a compiler or interpreter available for Linux. There are tens of thousands of precompiled packages available from the ARM64 Ubuntu repositories to install with the click of a button or a few keystrokes. Altogether, it forms a complete stack for creating and deploying AI-powered applications. In addition, NVIDIA has released additional SDKs called DeepStream and Isaac. Isaac is our robotics SDK and simulator, and DeepStream is for multi-stream video analytics. There's also an interactive profiling and debugging tools called Insight to help you tune the platform. Something wonderful about Jetson is that you can easily install and run the full versions of popular machine learning and deep learning frameworks on it, like TensorFlow, PyTorch, Caffe, Caffe2, MXNet, Keras, and others. Since Jetpack provides full CUDA support, including cuDNN, these are all GPU accelerated and able to get great inferencing performance running on board the device. This really streamlines migrating from your training environment to the edge device for inference. You can take your existing Python code using TensorFlow or PyTorch, for example, install those frameworks on any Jetson, the full versions of them even, and run that same code there. These all have the ability to work with Tensor RT for even better inferencing performance too. Deep learning frameworks aren't the only open source frameworks that you can run on Jetson. You can also install ROS, the Robot Operating System, Amazon RoboMaker, and AWS Greengrass for IoT. The L4T kernel supports Docker, so you can use Docker containers, another way people like to easily migrate their applications between the cloud and edge without extra maintenance. And for folks running multiple Jetsons in energy-efficient clusters, you can use OpenMPI for multiprocessing just like on servers. And this is just a small partial list. Check out the Jetson Zoo for pre-built installers, which there's a link on every Jetson desktop too. So we mentioned NVIDIA Tensor RT. It's NVIDIA's DNN inferencing accelerator library optimized for GPU. NVIDIA has cuDNN, which implements various network layers in CUDA, and Tensor RT operates at the network level. With knowledge of the network graph, it's able to perform additional optimizations like kernel fusion, which evaluates multiple layers at a time within the same CUDA kernel to reduce memory bandwidth usage and latency. It'll tune itself for the platform and can fully utilize the FP16 precision available on the Nano's GPU. Typically, you'll see multiple times speed up with Tensor RT. Folks will often start running with the native frameworks on Jetson still using GPU, and then optimize using Tensor RT to get the best real-time performance. It can load models from lots of frameworks like TensorFlow, PyTorch, Caffe, and many others via the Onyx Open Neural Network Exchange format. Next, we're going to take a look at some inferencing benchmarks run on Jetson Nano with Tensor RT. Jetson Nano can run a really wide variety of network models for doing everything from image recognition to object detection, segmentation, pose recognition, and others. Here's a small selection of models trained using a bunch of different frameworks that are running on board the Nano using Tensor RT. Interactive real-time frame rates are achieved even on the high-end networks up to HD resolutions. In particular, SSD MobileNet v2 is a widely used object detector used in a lot of applications. YOLO is another popular object detection model that we've benchmarked, and that's trained with DarkNet. UNet's a semantic segmentation model that classifies each pixel in the image. Semantic segmentation is like image recognition, but instead of just classifying the overall image like ResNet, Inception, and VGG do, UNet does per pixel classification, which is really useful for perception and autonomous navigation. Another cool network is SuperResNet, which has high-quality upsampling of images called super resolution that's useful for enhancing video of noisy, low-res sensors. OpenPose is what we ran for pose recognition, which extracts the positions and orientations in 3D of human skeletal feature of people in a video stream, like the locations of their arms, hands, fingers, face, feet, legs, and bodies. With this info, you can do behavior recognition and gesture recognition, for example, signaling with a robot or implementing collaborative behaviors in a factory or warehouse environment or your home. Okay, next let's take a look at some areas in the competition where you could apply AI with the Nano. Jetson powers deep learning and computer vision on many of today's most advanced autonomous robots, like those for last mile delivery, warehouse logistics and inventory management, precision agriculture, manufacturing and industrial inspection, retail, and home assistance robots. On these platforms, there are lots of high-definition, high-frame-rate sensors needing processed with low latency in order for them to function safely in their environment. It takes a lot of compute horsepower and flexible software in a compact size and power-efficient package to achieve autonomy on mobile platforms like these. To help everyone get started, we put together the JetBot, an autonomous AI-powered robotics kit with Jetson Nano. It's fully open source and includes all the software and hardware docs for sourcing the components and putting it together. The chassis is 3D printable and uses inexpensive parts, so you can build a whole kit for under $250, including the price of the Nano. JetBot's programmed through user-friendly Jupyter IPython notebooks. These contain the deep learning functions and logic to control the robot. Out of the box, it can do obstacle detection, object following, and path following using PyTorch and Tensor RT from a low-cost monocular camera feed. You can even collect new data from your environment right in the IPython notebooks and retrain the networks on board the Nano, so it's very easy to use and create new autonomous modes for. We've also released ROS nodes supporting the JetBot hardware, along with the Gazebo simulator model for it, so if you're a ROS user, you can bring ROS components to JetBot too. Let's watch a short video from the creator of the JetBot about what it can do.
So over here we have JetBot, which is an open source robot that we built using Jetson Nano. And the idea behind JetBot was to give people that wanted to start with AI or maybe AI with Jetson Nano a platform that they could just get up and running right away. You buy the components of the robot. We have everything on GitHub. So it's super easy to get started. It's all done in Jupyter notebooks. So we have like basic examples from just controlling from your web browser in Python. It's super easy to do. To more complicated examples like using AI for avoiding collisions. And then we go all the way to road following to have like kind of an autonomous car navigating a Lego city. So that's the basic idea, is that you can start with this platform. It's all open source, the hardware, the software, and then you can take what you learned, you can take the components even, and you could build something new, and who knows what that would be. It would be kind of up to you.
Another open source robotics kit that we put together is Jet Racer, which takes many of the concepts from JetBot to high speed. It's also built around the Nano and uses DNNs trained on board with PyTorch to autonomously drive around courses and racetracks as quickly as possible. There are versions that you can build with either 1/10th scale or 1/18th scale chassis for around $400. The technology has also been adopted into many other autonomous race car circuits out there, like Donkey Car and DIY Robocars, Musher, Race Car J, the MIT Race Car Project, and the F110th project from University of Pennsylvania. To easily develop and deploy software for intelligent robots and autonomous machines, NVIDIA has created the Isaac SDK that we mentioned earlier. It includes the Isaac Runtime Robotics Engine with algorithms and DNNs that we call GEMs for things like perception and autonomous navigation, SLAM localization and mapping, visual odometry, path planning and stereo depth, along with the high-fidelity Isaac simulator and suite of simulation environments called Isaac Gym, all fully optimized for GPU with CUDA and hardware graphics acceleration. You can use Isaac to train and deploy production autonomous machines and robots that require the best performance, and you can download the Isaac SDK and simulator from our site and deploy it to your Jetson. Also included with Isaac are multiple reference robot designs, like the Carter Delivery Robot and Kaya, to get you started. These reference designs include both the software, component lists, and plans for putting together the hardware. Here's an example pipeline of Isaac gems used by the Carter robot for navigation using a stereo depth camera and LiDAR for simultaneous localization and mapping, or SLAM. These are highly optimized with GPU acceleration to run in real time on Jetson and are camera ready. So for the smart cities category of the challenge, we have DeepStream, which NVIDIA's SDK for edge-to-cloud intelligent video analytics. Here we're showing a video captured from Nano, running 8 HD video streams simultaneously with object detection and time series analysis using DeepStream. DeepStream takes advantage of the Jetson's multi-stream video encoder and decoder hardware, along with the GPIO and Tensor RT to get the best performance out of the system. It's also optimized for zero copy, so there aren't any extra memory copies or transferred being made between processing steps. All of this is important to achieve the max throughput of the device, which as it turns out is pretty impressive for a low-cost, low-power board. This example is processing over 500 megapixels per second across 8 1080p streams, each at 30 frames per second. A ResNet-based detector is used for accurate tracking on each stream running at the same time. Here we're detecting vehicles, people, and baggage, and counting the number of occurrences of each type of object over time in each camera feed. If you plan on entering the Intelligent Video Analytics and Smart Cities category of the challenge, you can build your application with DeepStream and easily reconfigure the pipeline with different types of data streams, inferencing, and analytics processing that are tailored to your project. Okay, now we're going to switch gears to walk through the resources at your disposal to help you get started with the Nano, along with various peripherals and accessories available for it, and tips and tricks to using the board. There's already a lot of info out there on Jetson Nano available for you to use, like various tutorials for deep learning that we have and open source projects from the community. You can download the docs and software from our developer site, and we publish guides to the eLinux wiki too. There are lots of peripherals and accessories compatible with the Nano DevKit, and people have started coming out with some of the first customized carriers and enclosures for it also. And if you ever need support, we have a very active developer forum where you can ask questions and get help. Hello AI World is an easy to follow open source tutorial that we created to help you get started deploying deep learning on Jetson. It covers inferencing with image recognition and object detection, and comes with pre-trained networks for you to use out of the box and does live camera streaming. You can follow it in around 2 hours or less on your Nano, and during the tutorial you'll code your own image classification program in Python or C++ from scratch. It all uses Tensor RT underneath for great performance, and the core code is built into a library that you can easily use to make your own deep learning projects. Let's quickly step through the different parts of the tutorial to follow. The first thing to do is clone the repo from GitHub and build it on board your Jetson. During the build process, it will automatically download various network models and test images that you can use. Go to the URL shown here to get started reading the documentation on each step as well. Once you've compiled the code, we're going to classify some of the images that come with the repo, or you can download your own images to play around with. The repo includes built-in GoogleNet, AlexNet, ResNet, and VGG classification models that were trained against the ILS-VRC ImageNet dataset, which are able to recognize 1,000 different types of objects, including many different species of animals, fruits, vegetables, and different foods, natural scenes, along with man-made and household objects, vehicles, roadsides, and lots of other things. There's a link to the full list of objects it can classify in the tutorial, so you can check that list against what it's able to do. You can also retrain the networks on new data on board your Nano using PyTorch to be able to classify new objects. How the classification works is there's one output neuron in the network for each of the 1,000 classes, and each output neuron corresponds to the confidence value of that class. Then you pick the argmax, or the neuron with the highest confidence, and the index of that neuron corresponds to the object class that the network classified the image as. Okay, next we step through the code to make your own image recognition program in Python. Underneath, it's accelerated with Tensor RT on the GPU for real-time performance. First, you import the Jetson Inference and Jetson Util modules provided by the Hello AI World library, then parse a couple of command line options that provide the image to load and the classification network to use. Then load the image and network and perform the classification, which returns the class index that the image was recognized as, along with the confidence value between 0 and 1, 1 meaning 100% confidence in the classification result. You can map the class index to the text description or name of the class. The built-in models that were trained on the ILS-VRC ImageNet dataset of 1,000 objects will return a class index between 0 and 999, which can then be looked up from a label file that's stored on disk by the getClassDescription function. In this example, we print out the classification results to the console. However, there are other examples included with the repo that overlay the results onto the input image and save it back out to disk, like we saw in the previous slide. There's also support for native C++ in Hello AI World, and an object API is provided for each of the vision primitives that the Python bindings use underneath for optimum performance. The C++ code shown here shows the parts relevant to loading the network, classifying the image with Tensor RT, and outputting the result. This snippet is slightly abbreviated so it'll fit on the slide without the part that loads the image from disk, but even the full version is under 50 lines of C++ code and is quite simple to follow. Every example from the tutorial is provided in both C++ and Python, so you can use either language throughout. Next, we're going to run the inferencing in real time on a live camera stream. You can connect a camera to your DevKit and point it at different objects around the house or little props to see how it classifies them. It's pretty fun to play around with, and like all the steps, you can dig into the code from this program and see how to stream the camera as opposed to loading the images from disk. The cameras it works with are MIPI CSI, like the Raspberry Pi Camera Module V2, or USB webcams like Logitech C920. If you're using a USB camera, see the directions in the repo for changing it over to use USB webcams instead of MIPI CSI. The program can run up to the full rate your camera supports in real time, so for example, if you have a 30 Hz camera, it will process at 30 frames per second. The second phase of Hello AI World focuses on object detection, which builds on the concepts of image recognition. Object detection gives you the bounding box coordinates and is able to classify multiple objects per frame, as opposed to the image recognition networks used in the previous steps classifying the entire image. Object detection is really useful in robotics and analytics, where you need to know precisely where the things you're looking for are located in the frame. Like the previous examples, we start with processing some test images from disk and detecting various objects in them. You can look at the code for this program to see how the detections perform. It's mostly the same as the recognition, except that the detection network outputs a list of bounding boxes with a class and confidence value attached to each bounding box. There are a handful of detection models included with the repo, including SSD MobileNet and Inception, which were trained on the 90 class MS COCO dataset and run in real time on the Nano. Like the steps for image recognition, there's also a live camera app for object detection, which overlays the bounding boxes of the detected objects over the camera stream in real time, along with their class and confidence values. The SSD MobileNet and Inception models run at more than 20 frames per second on Nano in both Python and C++. You can see here a little demo video captured with SSD MobileNet V2 that shows it detecting various objects around the room. As mentioned, the built-in SSD models that were trained on the 90 class COCO dataset, so they can detect a bunch of different things out of the box, like humans, animals, vehicles, furniture, and other various household objects that you may have lying around or on your desk. There's a list of all the COCO classes included with the tutorial that you can look over too. Since the network typically outputs high-quality results, there's only a minimal amount of post-processing applied, just some really basic clustering of the bounding boxes, and is referred to as tracking by detection. Here's the Nano DevKit that all of this is running on. I have a MIPI CSI Raspberry Pi cam attached, and also a Logitech USB webcam with a longer cord that I shot this video with. The pre-trained models can also detect common electronics like TVs, monitors, laptops, keyboard and mice, and cell phones. Okay, the next vision capability covered in Hello AI World is semantic segmentation, which performs classification at the per pixel level using a fully convolutional network or FCN. These models take a pre-trained image recognition backbone, like ResNet 18 in this case, and convolutionalize them into a model capable of per pixel labeling. Segmentation networks are especially useful for environmental perception since you can discern scene foregrounds and backgrounds and get a dense representation of the world. It's commonly used in autonomous navigation for free space detection, which lets the robot know where it can and can't go, like for path following and obstacle avoidance. There's a bunch of built-in segmentation models that come with the repo that run in real time on the Nano and were pre-trained on different datasets, including cityscapes for urban environments, deep scene for off-road trails, multi-human parsing for pose estimation, Pascal VOC for common objects and animals, and Sun RGB for indoor scenes. Most of these models support 21 segmentation classes, and the performance on Nano is shown in the table here. As with the classification and detection primitives, there are static images and live camera demos provided for segmentation in both Python and C++ that you can run in real time on your Nano. In the final steps of Hello AI World, we show how to retrain classification networks on custom datasets so that they can learn to recognize new objects that may not have been included in the pre-trained models. This process is called transfer learning, and we can use PyTorch running on board the Nano to do it in a few hours on some decently sized example datasets of 10,000 plus images, like on different kinds of plants and cats and dogs. There's also a camera capture tool provided for collecting and labeling your own datasets, which typically can be trained much faster even on Nano because those are probably going to be smaller datasets. For large datasets and models, we recommend training on a host PC or cloud instance with discrete GPU, which are often used for computationally intensive training processes, as the Jetsons are optimized for low power inference. However, you can still get started with training on your Nano, particularly the PyTorch framework seems to work well because it's pretty memory efficient. Okay, that's it for now for Hello AI World. Next, let's cover some tips and tricks and walk through setting up a new Nano DevKit out of the box. The DevKit boots from a micro SD card, so all you need to do is download the SD card image from our website, which already includes all of the Jetpack components pre-installed, and flash the image to your micro SD card from any PC that has an SD card slot. You can easily flash it with a common tool called Etcher that runs on Windows, Mac, or Linux, and there are a number of other tools out there that can do it as well. When you're done flashing, you take the formatted SD card out of your PC and insert it into the slot on your DevKit. The micro SD card slot is located on the underside of the Nano module, on the side opposite facing the connectors. It's recommended that you use at least a 16GB UHS-1 micro SD card. The faster the class of SD card, the faster it'll boot up and load. And you can use as large a micro SD card as you want. There isn't a limit on the storage capacity, and your user partition will automatically be expanded to fill the entire SD card. You can also attach a solid-state drive with the USB 3 to SATA adapter for extra storage or faster read-write speeds. As far as connections go, you can use the DevKit either in a headless configuration and connect to it over serial port or Ethernet via SSH from a host PC, or by plugging in an HDMI or DisplayPort monitor along with keyboard or mouse and use it like a normal desktop and develop right there on the Nano. Next, let's talk about powering the DevKit. There are multiple ways that you can power it, which makes it quite versatile to use in projects. You can use a micro USB adapter capable of delivering 2 amps, ideally 2.5 amps, like the ones listed here and in the Jetson Nano supported components list. If you've connected a bunch of peripherals to the board, like USB devices or unpowered USB hubs, and are running a demanding computational load, then you may want to step up to using the DC barrel jack with a 5V 4A power supply. If you want to use the DC barrel jack, remember to fit a standard 2.54mm jumper on the J48 power select header. This switches the board between accepting power from the micro USB port to the barrel jack. In this mode, you can also connect a power source to pins 2 and 4 on the J41 expansion header, 3 amps per pin or up to 6 amps total. Pins 2 and 4 should be 5V DC, and pin 6 should be connected to ground. You can also power the Nano from a battery pack, like some of those portable USB battery packs with built-in regulations seem to work pretty good. Now there's actually a fourth way to power the board, and that's power over Ethernet. You can use a PoE hat or use a voltage regulator to take it from the 48 volt standard that you see in Power over Ethernet down to the 5 volts that the Nano uses. Also, I called out on the last slide that the board will automatically turn on and start booting up once power is applied. You can change that behavior by fitting a jumper to pins 7 and 8 on the J40 button header, which will disable auto power on, and then you'll need to short pins 1 and 2 on J40 to power it up. In addition to the power on signals, J40 also has pins for resetting the board and entering it into recovery mode. You can connect momentary push buttons to J40, which are more convenient to press, or you can just use jumpers on them when you need to. An extension of the discussion of power supplies is the power modes that the board is able to run. Nano has 5 and 10 watt power modes, and by default it'll boot up in 10 watt mode, which gives it the best performance. NVP model is a software tool used to change power modes and tweak profiles depending on your use case. You can run the NVP model-q command to query the current mode and NVP model-m to change modes. When you change modes, it'll persist after reboot, and you can run the Jetson clock script to lock the clocks to their maximums for the current mode. You can define your own custom power modes too. They're located in the etc nvpmodel.com file, and they look like the configuration shown here, listing the various maximum clock frequencies. There's also a GUI widget located in the top right of the Ubuntu screen that will allow you to change the power modes from the UI. Now, to keep an eye on system performance, you would typically use a program like Top or the Ubuntu System Monitor. However, there's a lot more information available in Nano, so we have a tool called Tegra Stats, which displays all the stats that you wouldn't get otherwise, like the utilization and frequencies of the GPU and memory controller, temperatures from the thermal sensors, and power measurements from the onboard INA sensors. The INA sensors measure the power consumption across different power rails, including the usage from the CPU and GPU, and the overall usage as well. I recommend that you try running this in the background while you're benchmarking or profiling your application, so you can keep an eye on the core utilizations, memory bandwidth and consumption, and the dynamic clock frequencies to scale at runtime depending on workload. There's also some open source tools from the community like JTOP, which visualize the output from Tegra Stats. The Nano DevKit has a 40-pin expansion header, J41, similar to what's found on the Raspberry Pi, and is compatible with many of the same peripherals and hats. It's supported in Adafruit's Blinka Python library and Seed Studio's Grove library, which all told support over 400 devices and sensors that you can use. By default, the Nano's 40-pin header is configured to expose 2 SPI ports, 2 I2Cs, UART, audio, GPIOs, 3.3 volt and 5 volt power pins. The protocol interfaces like SPI, I2C, I2S, and UART are referred to as special function units or SFIOs. Using the pin muxing tool, you can reconfigure the Nano's device tree to change these SFIO pins over to GPIO or vice versa. To access the GPIO pins directly, there are a few APIs you can use from user space for doing this. Jetpack includes the Jetson GPIO library from Python, which provides the same interface as the RPi GPIO library, so assisting code and drivers using RPi GPIO automatically can use the GPIO on Nano too. For using GPIO from other programming languages and shell scripts from the command line, the GPIO pins are exposed in sysfs under sys class GPIO directory, which is the standard location for these in Linux. You can read or write to these files using cat and echo, or the file IO APIs from any programming language like fopen and fread in C or C++. And actually the Jetson GPIO Python library uses these sysfs files underneath too. The special function units typically have their own software interfaces. In the case of I2C, there's a cross-language API called libi2c for C, C++, and Python, and SPI has the standard SPI dev user space module available. As mentioned, there are hundreds of compatible devices and hats that you can plug into the 40-pin expansion header. However, there are lots of other accessories that have already been created for the Nano, including a number of 3D printable enclosures for the device, aftermarket carrier boards with additional I/O, and sensors like CSI imagers and stereo cameras. You can find links to these on the eLinux wiki and from our ecosystem partners, and we anticipate a lot more becoming available this year. The camera header on the Nano DEVKIT is compatible with the Raspberry Pi camera V2, and drivers for the IMX219 sensor that it uses are included in Jetpack, so it works out of the box. Leopard Imaging and Econ Systems also have MIPI CSI cameras available that work with the Nano too. Since Jetson is frequently used to process live camera streams, let's talk about how to capture video from software. NVIDIA has an optimized library called Argus, which is part of the L4T Multimedia API, which provides image acquisition for MIPI CSI sensors. MIPI cameras have the benefit of being chip-to-chip and being ingested directly into the Jetson hardware without needing to go through the CPU or have extra memory copies. Argus is optimized for zero-copy and low-latency multi-camera applications. There are Argus APIs for C++ and a wrapper library for Python that you can find on our GitHub site. We also support GStreamer in Jetpack, and we provide a number of hardware-accelerated elements to use in GStreamer pipelines for accessing features like the camera interfaces and video codecs. Here's an example pipeline that you can launch from the command line that uses our NV-Argus camera source GStreamer element, which does camera capture with libargus underneath. With GStreamer, you can patch together a lot of different pipelines for compressing the video and recording it to disk, or compressing it and streaming it out to a remote host over the network via RTP or RTSP, or lots of different things like receiving IP cameras over the network and decompressing those. There's also V4L2, or Video for Linux 2, which is a standard video API for Linux. V4L2 cameras get mapped to a device node under Dev Video, and on Jetson, MIPI CSI cameras will show up there too. V4L2 also supports USB webcams and various other camera protocols, and you can use it by either accessing a Dev Video device file from any language, or by using a wrapper library like those mentioned here for C, C++, and Python. There's also a GStreamer element for V4L2 camera capture called V4L2 source, so it's easy to swap that out for USB webcams in your GStreamer pipelines. Another important part of Jetson's multimedia capabilities are its multi-stream hardware video and decoder engines. Nano can decode up to 8 1080p30 H.264, H.265 streams and encode up to 4 1080p30 H.264, H.265 streams simultaneously. It can also decode 2 4K-P30s and encode a 4K stream simultaneously, and in addition to H.264, H.265 compression, it supports VP8 and JPEG profiles for encode, and VP8, VP9, VC1, MPEG-2, and JPEG profiles for decode. At runtime, you can mix and match the profiles, number of streams, resolutions, and frame rates shown in the tables here, up to the aggregate bandwidth of the encoder and decoder. The encoder and decoder are independent hardware units, so they can each be utilized to their fullest at the same time without impacting the performance of each other. To use these codecs from software, there are a couple APIs for them that NVIDIA provides through Jetpack. First, there are accelerated GStreamer elements available for each of the profiles that do encoding and decoding, for example, OMX H.264 and OMX H.265 Here are some example GStreamer pipelines that encode an H.265 video to disk in MKV format, and then a second pipeline that decodes the MKV file and decompresses it from H.265. You can also easily connect the camera elements from the previous slide to the encoder and record it or stream out your camera video. There are a lot more example GStreamer elements and pipelines included in our L4T Accelerated GStreamer User Guide that you can download from our developer site. And to see all the GStreamer elements available in your system, you can list them with the GST inspect command. There's also a hardware video image conversion and compositor engine available exposed in GStreamer through the NV-VidComp element for doing color space conversion, cropping, rescaling, rotation, and temporal noise reduction in hardware. The second set of APIs that NVIDIA ships for the codecs are V4L2 extensions from Jetpack's L4T Multimedia API that support H.264 and H.265 compression and decompression. These can be used directly, in which case the file I/O and depacketing needs to be performed by the user, or they're also exposed as GStreamer elements that can be integrated into a complete pipeline. One final topic we're going to cover today is Jetson's Unified Memory Subsystem and Zero Copy. All of the processor cores in Jetson share the same common memory controller and physical DRAM, including the CPU, GPU, camera ISPs, codecs, multimedia engines, and high bandwidth I/O controllers. That means you don't need to have extra memory copies between the different cores. They can simply reference the same memory used in previous processing step in the pipeline. Eliminating these extra memory transfers is called zero copy, and it greatly reduces latency and the amount of memory bandwidth wasted, freeing up the bandwidth for other purposes. Ultimately enables you to process more streams at the same time, which coupled with the optimized inferencing with Tensor RT is one reason why Nano is able to handle 8 HD streams simultaneously. When you're working on the GPU, you may be familiar with the CUDA memcopy function, which is used to transfer data between the CPU and GPU. On typical PC systems, the GPU is connected over PCI Express and has its own discrete memory, so it doesn't share memory with the CPU and needs to shuffle around data sometimes. However, on Jetson, you don't need to use CUDA memcopy because all the memory in the system is shared and you can just map the same pointer into the GPU's address space. There are a couple of APIs in CUDA for accomplishing zero copy. You can use mapped memory with CUDA host alloc and CUDA host get device pointer, or you can use CUDA's more recent unified memory feature with the CUDA malloc managed API, which is also able to implicitly handle synchronization. Consult the CUDA documentation to determine which approach is more beneficial for you and your application. Other engines can use zero copy in addition to the GPU also, like the camera ISP and codecs with EGL streams, which are interoperable with OpenGL and CUDA too. So you can do zero copy between more than just the CPU and GPU, practically the whole system. It's highly recommended to take advantage of these techniques when optimizing your application to achieve the peak performance and utilization from the device. Okay, so that brings us to the end of today's presentation. Thanks again for joining us, and we wish you the best of luck in the challenge and look forward to seeing what you create with AI. Later, we'll post the PDF of these slides with clickable links so you can easily find all the resources we've covered here. Okay, next we're going to get set up for Q&A, so if you have any questions, enter them into the Q&A window now. We'll stick around for as long as we can, but if we don't get to your question, please feel free to post it to the forums and we'll get back to you soon.
So let's start. So there was some general questions about, I'm doing so-and-so project. Where does that project fit into the 3 categories of the challenge? So I thought it would be good if we just did a quick overview, maybe some examples of what type of projects would fit in each. So the robotics category generally would require some type of mechanical actuation in it. It doesn't need to be a mobile robot like the JetBot per se. It could be like a little robotic arm or some type of robotically triggered device that triggers a servo or an actuator. But generally that would fall into the robotics category. The intelligent video analytics category is mostly be for smart camera-like applications that are using deep stream. They don't need to be per se like traffic monitoring like the examples that we showed, but if you're doing some type of analytics on video around your house or home, there's like this smart doorbell application example that we have on our Jetson Nano project site, that could, example, fall under the IVA category. And then finally, there's this more general AIoT category, the artificial intelligence of things, and that can be, very broad. Anything that is taking in some type of data and doing, some type of machine learning or computer vision or some type of processing on it that you're either using locally or connected to the broader internet. It could be a local network. Doesn't necessarily have to be connected over a wide area network. So hopefully that clears it up. If you don't really know where it fits, you are welcome to post to the forum and we'll try to help you and get back to you where we think it could best be submitted to. Okay, so now for some more technical questions per se about the Nano. There was a question, does the Nano work like any other NVIDIA video card that you may be familiar with, like a GeForce card in your PC? Yes and no. The GPU on the Nano is very much just like a GPU in a PC. It can run OpenGL graphics and any Linux stuff and CUDA and all of the typical graphics. The difference with the Jetson is it has all of the other components in there, like the CPU and the memory, and is the complete SBC. It's not just the graphics card. There's a question about different ML frameworks and how do I install TensorFlow, or how can I install PyTorch? There's a couple different frameworks folks were asking about. We do make pre-built installers, these pip wheels available for the popular frameworks like TensorFlow and PyTorch, and you can find those on the Jetson Zoo. That's a page on the eLinux wiki that's linked to from every Jetson desktop. And basically you can just automatically download installers. You can also build other ones from source, which is the typical way if you don't already have a binary installer. There were a bunch of questions about Wi-Fi cameras, or basically IP cameras that you stream over the network, whether it's a wired connection or over Wi-Fi. And you can use those on Jetson through GStreamer if they support RTP or RTSP, which are common IP camera streaming methods. And if it's a Wi-Fi camera, basically that just means you need to have a Wi-Fi adapter added to your Nano so that you can connect it to the same network that the camera is connected to. Now, I will say there are a lot of IP cameras out there that have vendor-specific protocols, or maybe some other protocol libraries that you need to install. In that case, you would just need to install the libraries for those cameras onto your Nano and use those interfaces. But in general, it's a good bet. If they say they support RTP or RTSP cameras, those can work pretty easily. And RTP, RTSP cameras are also supported natively in DeepStream in addition to GStreamer. Another cool thing is you can set up your Nano to act like an RTP or RTSP camera, or a streaming source. You can take in video from a camera locally and then stream that video back out over the network to another remote host using the same GStreamer elements. There was a question about how do if I get my Nano all set up and install a bunch of stuff and may want to make a backup of the SD card image in case I just want the backup, or I want to do some other modifications and maybe have that checkpoint to roll back on, or when NVIDIA does release new Jetpack images, you want to make a backup of that. All you have to do is take the SD card image out of your Nano and then plug it into your PC that you flash it from. If it's Linux PC, you can use like the DD command and it'll just back up the entire contents of that SD card image, and then you can reflash it with the Etcher tool or what have you. And I think there are tools available for Windows and Mac that do a similar thing. Basically, you're just cloning the SD card image, and then you can reflash it at a later time. There's a question, can I boot Nano from a USB drive or like a solid state drive? Yes, you can do that. You have to go into the extlinux.conf file and change what device the kernel boots from. And there's an article on Jetson Hacks about doing that. I don't know if I mentioned Jetson Hacks, but it's a very popular blogger that we like to work with, who posts a bunch of other videos and tutorials about using the Jetson. So if you haven't already checked out Jetson Hacks, he does a really good YouTube channel. Can I run the Nano headless, or do I need to have a display attached to it? You're welcome to do either or. The Nano can be like a whole little PC, and you just plug in HDMI and USB keyboard and mouse, and it's just like working on a normal desktop. Or you can run it like a traditional embedded board where it's only connected over Wi-Fi or Ethernet, and you basically just SSH into the board. You can also set up the Nano completely headless if you don't even have an extra HDMI or DisplayPort monitor. In that case, you just connect it to your PC over the micro USB connection, which emulates a UART terminal. So you would just connect to it from PuTTY, for example, and then that would allow you to set up your user configuration. And then after you did that, it would activate SSH and you could connect to it over the network. There was also a bunch of questions about, regarding networking. Can the Nano act as a Wi-Fi access point? And the answer does depend on which Wi-Fi dongle or adapter you're using. If that Wi-Fi device does support access point mode, you can enable it just the same way that you would turn on access point mode on other systems. Generally, that's using the host APD daemon that you can install through Linux. So you can just install that and enable it in your Wi-Fi driver if necessary. But generally, you can just check if that particular Wi-Fi device that you want to use supports access point mode. There was some questions about stereo cameras and other depth sensors. So I guess I'll just cover those all at one time. Which stereo cameras can I use, or what depth sensors, either active or passive? So the most common stereo camera that's used with the Jetson is called the Stereolab Z. It's a USB 3 camera that does the stereo vision processing in CUDA. So it's a really good match for the Jetson. And there's the full-size Z, which is like this big, and then there's a Z Mini. There's also stereo cameras from Econ Systems and Duo 3D that are supported on the Jetson. And there's a bunch of like these time-of-flight RGB depth cameras as well, like RealSense D35i, Structure.io sensors that I've seen used on the forums. So, and in general, if you have a USB peripheral that you want to use, as long as it has a driver that supports a recent Linux kernel version like Linux kernel 4.4, then it should be good to go. You might need to install the driver if that driver is not natively built into Linux, or a lot of cameras just work because they're what's called UVC compliant, which means it works with the Video for Linux 2 interface. Others, like the RealSense, for example, you would need to install like the lib RealSense, or like the Microsoft Kinect. There's this lib FreeNect 2, I think, is the current version that you can install to get those working. Along those lines, there were some questions about using ROS, the robot OS, and how do you install that and what versions are supported. So the way you should install it is just the normal way from the ROS website, because they do maintain ARM64, ARch64 builds now. And the version that is supported is ROS Melodic, because that's the version for Ubuntu 18.04, which is also the version that the Nano currently runs. And we do have ROS packages for deep learning available too, and we also, as mentioned, have the ROS packages for JetBot. Question just came in about regarding the JetBot and JetRacer is, do they use different images? And yes, the JetRacer does use a slightly different image than the JetBot, just because the IPython notebooks that it uses and also the underlying hardware drivers are slightly different, but is mostly the same. And the instructions for building your own JetBot or JetRacer image are covered in those wikis too. So the pre-built images, as with the main Nano image, are really provided for convenience. If you do want to, tweak and tailor your own Nano image, you can pretty easily do that just by following those instructions. Or if you want to create your own master Nano image, you can use what's called the NVIDIA SDK Manager, which would allow you to pick and choose which components you want to flash to the Nano, as opposed to, just pre-installing everything. In general, just the main Nano image is much easier to use. Okay, so let me look for some other questions here. What can I use to train my own neural network? Let's say, we do provide a bunch of pre-built networks that are trained on common objects, but as part of, a project, it could be very conceivable you want to train it on some specific source data. In that case, you can train smaller data sets on the Nano, depending on how long you want to wait. The examples from the Hello AI World tutorial typically run overnight for multi-gigabyte data sets that train for 30 training epochs, or you can either use smaller data sets or train it for less amount of time. But for really large data sets, 20 plus gigabytes or so, you would probably want to look into using either a cloud instance with GPU like an AWS or Microsoft Azure instance that has a larger GPU, because that's really what most data scientists are using for training neural networks, either in like TensorFlow or PyTorch. And we will be giving away some credits throughout the competition to some applicants who want to do that. Or if you have like a PC that has a discrete GPU in it, or like a laptop that has an NVIDIA GPU, you could run it on there. Along those lines of deep learning and machine learning, there's a question of, is it a requirement to use deep learning and machine learning in this competition? And it is not. Artificial intelligence is more than just deep learning or machine learning. You can do traditional computer vision methods with like OpenCV, or NVIDIA also has VisionWorks, which is an accelerated vision library that's highly optimized for GPU. And some example algorithms you could run are like SLAM, or different object detectors or trackers like optical flow algorithms, things like that. Generally, you might see a mix and match of both CV and deep learning algorithms used together. Also along those lines was a question of, can I run multiple deep learning algorithms or neural networks at the same time? Or extrapolating that, can I run computer vision algorithms and deep learning networks at the same time? And yet in most cases, the Nano is very much capable of running multiple at the same time. If you're running a really heavy network that's already taking most of the performance, you would have to make sure you have enough performance to accommodate both. But in general, if you're doing like image classification using a ResNet 18 or MobileNet network, which can run at 60 frames per second, that should leave you more than enough room also to host other computer vision methods in the background. So it's basically just about, can you get enough performance out of both? Let us take one final question here, since we're at the top of the hour. And again, if you have more questions, we're happy to hang around the forums, and you can post them there. There's a question about, what programming languages can I use on the Nano? And as mentioned in on one of the earlier slides, basically anything that has a common compiler available in Linux. Most common we see are C, C++, and Python, but you could also use things like Mono C# or Rust, or you can either do web servers like with PHP, or anything that has these Linux packages available, you can program in. And there's lots of different things out there depending on what you want to use. Again, Python and C++ seem to be the most popular. So thanks again for joining us today, and we really look forward to the competition and supporting you guys throughout, and best of luck working on your projects, and we'll see you around the forums. With that, I will turn it back to Monica. So thanks again, everyone, for joining us.
Thank you so much, Dustin. That was a great presentation. I hope you all post your projects to the DIY Intelligence contest on Hackster. and I look forward to seeing what you post. So thanks again for coming to the webinar, and I'll be looking for your projects on Hackster. Thanks again, Dustin.